Ladies and gentlemen, it is a great pleasure to present our recent study on global and local fracture behavior in a brittle solid with a set of pre-existing small-scale cracks at Virtual Force International Conference on Structural Integrity. It is presented by Kunihiro Nagasawa in collaboration with Koji Uenishi from the University of Tokyo, Japan.
In seismology, one single large-scale fracture region is usually considered as a model of an earthquake source, for example the 2014 Nagano-ken Hokubu Kamishiro Fault Japan earthquake. However, such a single large-scale fault model generally causes only one seismic event, so it is hard to elucidate mechanisms of a cluster of earthquakes like the 2016 Kumamoto Japan earthquakes. For understanding these complicated seismic events, not only global observations of large-scale material behavior, but also more local tracing of smaller-scale fractures is needed. In this study, by using a technique of dynamic photoelasticity, the evolution of fractures and waves is experimentally traced in a two-dimensional linear elastic brittle specimen that has a set of pre-existing small-scale parallel fracture regions. The small-scale fracture regions of cracks, modeling a large-scale geological normal fault plane, are prepared by the digital laser cutter. Thus, the purpose of this research is to clarify the fracture mechanism of the small-scale pre-existing crack model experimentally and numerically, and to shed light on more complicated dynamic fracture phenomena such as seismic clusters.
For experimental observations, a high-speed digital video camera was prepared and the fractures of rectangular polycarbonate specimens, which are one of the brittle materials, were set to tensor testing machine with photoelastic experimental equipment and traced with the high-speed camera at a frame rate of 1500 frames per second so as to visualize dynamic elastic waves transmitting in the body. In the case of the specimen having pre-existing cracks which are arranged perpendicularly to the tensor direction,
first, primary fracture proceeded from the underside to the upper side. Almost at the same time as the initial crack reaches the upper end, secondary fractures were formed in the opposite direction of the initial fracture.
Surprisingly, one of the secondary fractures progressed to some extent,
and soon was arrested around the middle of the specimen, pulsing for about 200 microseconds.
Eventually, the fracture split the specimen totally in half despite no additional static load.
Here, to summarize this fracture propagation event, primary fracture propagated at first, then secondary fracture was generated and progressed with an 80 microsecond short break at the half of the specimen. Finally, the secondary fracture was split without any external loading after the primary fracture propagation. The secondary fracture is not to be considered that this was caused by static stress, but by dynamic wave propagation, because this fracture began to develop after the primary fracture had completely broken the specimen. This result is supplemented by numerical calculations based on the Finnish difference method with a space-temporary second-order accuracy, assuming a homogeneous, isotropic, and linear elastic material with mass density 1,200 kg per cubic meters, shear modulus 820 MPa, and Poisson's ratio 0.37. In the calculation, longitudinal, shear, and radial wave speeds are 1,820 m per second, 827 m per second, and 775 m per second. For visual clarity, dynamic stresses generated by the primary fracture are shown in the simulation. We can see the fracture propagation and also rafter front wave which characterizes dynamic crack propagation can be seen at 40 microseconds. After that, when the dynamic elastic waves reach the opposite boundary, you can see where the stress is concentrated. This is exactly where the secondary fractures were initiated in the former experiment. Then, the radial surface wave travels along the free surface of the specimen. Is reflected at the edge and then propagates along the secondary fracture region. It can be considered that the secondary fracture repropagation was caused by the reflected radial wave.
In this way, it has become clear both experimentally and numerically that the specimens which have pre-existing cracks can generate not only one single large fracture, but also secondary additional fractures.
Other experiments indicate that the global fracture behavior significantly depends on the initial inclination angle and distribution pattern of the set of parallel cracks. This is a specimen whose pre-existing crack inclination dip angle is 70 degrees. First, the primary fracture will develop. Then, secondary fracture occurs like the former experiment. Finally, the fracture propagates and the specimen is split totally. This behavior looks like that of the former vertical dip angle one, but it is slightly more complicated that the direction of the crack growth is a little curved. Next, I will introduce an example when the dip angle is as small as 15 degrees. Under static loading, the primary fracture grows quasi-statically, connecting the tips of the pre-existing cracks. Contrary to the simplicity of primary crack growth behavior, in this case as well as the experiment presented before, the main fracture stopped before the crack completely split the specimen, and almost at the same time, secondary cracks began to move dynamically. In the example shown here, the secondary fractures branched at the end, resulting in the destruction of the entire specimen. It is concluded that in the case of pre-existing cracks that are more vertically inclined with respect to the quasi-static external load applied by a tensile testing machine, the main fracture is prone to develop dynamically, and then the secondary fractures appeared at space-temporally remote distances from that main fracture. The secondary fracture extends also dynamically into the direction opposite to that of the main fracture. On the other hand, in the case of smaller inclination angles, the main fracture tends to evolve quasi-statically. Nevertheless, in both cases, it is found that fracture can jump without difficulties in brittle solid having a number of small-scale cracks, which implies that such small-scale cracks may play an important part in the generation of a cluster of seismic events.
Thank you for your kind attention.